Hi, welcome to educator.com. We're going to talk about the chi-square test of homogeneity. Previously, we talked about the chi-square goodness of fit test. Now we're going to contrast that with this new test. It's still a chi-square test, but it's a test of homogeneity now. We're going to try and figure out when do we use which test. Because we're testing a new idea, we're not testing goodness of fit, we're actually testing homogeneity, similarness. We're actually going to have slightly different null hypotheses and null and alternative hypotheses. So we're going to talk about how those have changed. Then we're going to go over the chi-square statistic, and also finding the expected values is going to be a little bit different in tests of homogeneity. Finally, we're going to go through chi-square distributions as well as degrees of freedom and the conditions for the test of homogeneity. When can you actually conduct this test sort of statistically legally? Okay, so the first thing is, what is the difference between the test of homogeneity and the test of goodness of fit? Well, remember in the goodness of fit hypothesis testing, we wanted to determine whether sample proportions are very different from hypothesized population proportions. One way you could think about this is that you have one sample and you're comparing it to some hypothetical population. In tests of homogeneity, and that's why it's called goodness of fit. It's about how well these two things fit together. How well does the sample fit with the hypothesized proportions? In tests of homogeneity, homogeneous means similar, right? That they're made up of the same stuff. In tests of homogeneity, we want to determine whether two populations that are sorted into categories share the same proportions or not, right? And here, you could also substitute this word population here, because ultimately we're using the sample as a proxy for the population, right? So here we have two populations, and we want to know whether those two populations are similar in their proportions or not, right? We're not comparing them to some hypothesized population. We're comparing them to each other. And so really, you could think of this as an analogy. You could think of their relationship by using an analogy from the one sample to the independent samples t-test. In the one sample t-test, we had one sample and we compared it to the null hypothesis, right? That was when we would have null hypotheses such as mu equals 0, or mu equals 200, or mu equals -5, right? Versus in independent samples, we had two samples. And we wanted to know how similar they were to each other, right? Or how different they were from each other. And our null hypothesis was changed to something like mu sub x bar minus y bar equals 0, right? That they're either made up of the same mean or different means, right? And in a similar way, the goodness of fit chi-square is really asking whether this proportion in my sample, I'll just use black and white, right, is similar to the proportion in our population, right? So that's how I'm comparing it. This is my null hypothesis in some ways. In our test of homogeneity, we have two samples, two populations, two samples that come from two unknown populations, right? And we want to know whether these have similar proportions to each other. And so that's going to be our null hypothesis, that these have the same proportions or have different ones. So our null hypothesis is similar proportions. All right. And so in that way, I hope you could see that goodness of fit and homogeneity, they're ideas that we've looked at before, comparing one sample to a hypothesized population or comparing two samples to each other. But we've looked at it before, not with proportions, but with means, right? And now we're looking at it with proportions. Okay, so since we're looking at proportions, we should have hypotheses about proportions. So the null hypotheses look something like this. The proportion that falls in each category, into each category is the same for each population. So however many categories you have, so let's say we have, 3 categories. If we believe that they are the same, then these should roughly have the same proportions. Right? So these have similar proportions. It doesn't actually matter what the proportions are. It could be 90-10. It could be 80-10-10. It could be 75-25. Like, whatever the proportions are, we're saying they're similar for each population. And whatever category is 75% of this population, that category will also be 75% of this population. The alternative hypothesis says this: for at least one category, the populations do not have the same proportions. So just like before, we're now talking about differences, but the differences are really in the proportions, the the population's proportions. So just to give you an example, here's a problem, and let's try to change it into the null hypothesis as well as the alternative hypothesis. So according to a poll, 406 Democrats said they were very satisfied with candidate A, while 510 were unsatisfied. However, 910 Republicans were satisfied with candidate A, while 60 were not, right? And in a chi-square test of homogeneity, we could see whether the proportions of Democrats and Democrats who are satisfied are similar to the proportions where Republicans who are satisfied versus unsatisfied. So let's draw this out first. So here we have about 400 Democrats saying they're satisfied, while 500 saying unsatisfied. Let's put satisfied in blue, and so that's a little bit less than half. And the unsatisfied people are a little bit more than half, right? So this is the Democratic population. That's what they look like. The Republican population looks very different. So here we see most of the Republicans being pretty satisfied, and only a very, very small minority being unsatisfied, right? And so the question is, are these two similar? Are the proportions that fall into each category, satisfied or unsatisfied, the same for each population, or are they different? The null hypothesis would probably say something like this: the proportion of satisfied and unsatisfied people, I guess, are similar, are the same for Dems as well as Republicans. The alternative hypothesis says for at least one category, either satisfied or unsatisfied, Dems and Republicans are do not have the same proportion. Okay, so note that in the case of 2, once one category changes, once the proportion of one category changes, the other one automatically changes, right? So if we somehow were able to change how satisfied the Democrats were with candidate A, we would also see the proportion of unsatisfied people just automatically change, right? So That's in the case of 2 categories. But in the case of multiple categories, maybe 2 might change, but the others may not change, right? So in that way, this would be a more general way of saying the alternative hypothesis. Okay, now let's talk about the chi-square statistic. Now, the nice thing about the chi-square statistic is that it's the same as the goodness of fit test. We use the same idea. So chi-square is going to be observed frequencies and the difference between that and expected frequencies squared over the proportion of expected frequencies, right? But here, there's just one subtle difference. Before, it was for each category. Now we have different categories in different populations, right? So we not only have like category 1 and category 2 and category 3, so on and so forth, but we also have population 1 and population 2, at least, right? And so we have multiples of observed frequencies, and so what do we do, right? Well, what we do here is that we consider each of these combinations of which population you're in and which category you're talking about. Each of these are going to be called cells, right? And so we do this for each cell. So I will go from 1 up to the number of cells. And how do we get the number of cells? Well, the number of cells is really how many populations, right? And that's usually shown in columns, times how many categories. And that's usually shown in rows, right? So you could also think of the number of cells as columns times rows, how many columns you have times number of rows. But really, the idea comes from how many different populations you're comparing, because in a chi-square test of homogeneity, you could actually compare 3 or 4 populations, not just 2, and how many categories you're comparing. So in order to use the chi-square formulas, it's often helpful to set up your data in a particular way. Often these formulas will refer to rows and columns, and so you really need to have the right data in the rows and the right data in the columns in order for any of these formulas to be used correctly. So it's helpful to set up your data in this way. Whatever your sample 1 is, you want to put all of the information for sample 1 into a column, right? So here I put sample 1, it's a generic sample 1. It could be college freshmen or Democrats or mice who got a certain drug, whatever it is. This is sample 1. And these are the people in sample 1 who fell into category 1. These are the people in sample 1 who fell into category 2. And these are called cells, right? That's a cell, and that's a cell. When you add these frequencies up, you should get the total number of people in sample 1, right? So in that way, all the information from sample 1 is in a column. Same thing with sample 2. All the information from sample 2 should be in a column. These should be the entire sample broken up into those that fell into category 1 versus category 2. And then the total gives you the total number of cases in sample 2. If you had sample 3 and 4, they would follow that same pattern, and all their information should be in one column. On the flip side, when you look at rows, you should be able to count up how many people, how many cases were in category 1 period, right? And so if you count them up this way, this isn't a sample, but it's just how many cases in the entire data set that you're looking at are in category 1. And if you look across here, this is how many cases in the entire data set fall into category 2. And finally, if you look at this total of totals, what you should get is the entire data set all added up, right? So let's try that here with the Democrats and Republican example. So I'm going to put Democrats up here, Republicans up here, satisfied and unsatisfied. And all I need to do is make sure I find the correct information and put it into the correct cell. 910 satisfied, 60 are not. When I add this up, I should be able to get the number of how many Democrats total that are in this sample. So this is 916. For Republicans, this is 970. So we have slightly more people in our Republican sample than in our Democrat sample, and that's fine. If I add the rows up like this, if I get the row totals, what I should get is just the number of satisfied people, period. And it sort of doesn't matter whether they're Democrats or Republicans. So I should get something like 1316, and this should be 570. All right, and so if I add these two up, that should equal these two being added up, right? Because I'm just adding these four numbers up in a different order, right? So that should be 1886, 1886. All right, great. So we have 1,886 in our total data set, right, across both samples. And we know how many people were satisfied, how many people were unsatisfied. We also know how many Democrats we have and how many Republicans we have, and all the different combinations, right? Democrats who are satisfied, Democrats unsatisfied, Republicans satisfied, Republicans unsatisfied. So this is a great way to set up your data, because that's really going to help you figure out expected frequencies, which is a little bit more complicated to figure out in tests of homogeneity. Not too much more complicated, but just a little bit more. So here's how we figure out expected frequency. So once you have it set up in this way, Democrats, Republicans, satisfied, unsatisfied, right? Once you have it set up in this way, here's the formula you use for expected frequency. So E is going to equal basically the proportion of people who are in one particular category. So I just want to know how many people tend to be satisfied, period. I don't care whether they're Democrats or Republicans, just in general, who's satisfied, right? So that would be the row total, right? So the row total over the grand total, this one right here. This will give me the rate or the proportion of just the general rate of who's satisfied, who tends to be satisfied. Is it 70% tend to be satisfied, 20% tend to be satisfied, 95% tend to be satisfied? What's the general rate? And then I'm going to multiply that by the total number of the sample that I'm interested in. So maybe I'm interested in this Democratic sample, so I would get the column total. So that's the general formula, but I want to show you this in a more specific way. So let's talk about the expected value of Democrats who are satisfied, right? So that would be the satisfied total over the grand total, right? So this gives us the rate of being satisfied, just in general, what proportion of the entire data set is satisfied. And then I'm going to multiply that by however many Democrats I have. So Democrat total. So I could write it in this way, but what ends up is that this is just a more general way of saying this example. So when I say Democrat total, it's the same thing as saying column total, right? And when I say row total, it's really the same thing as saying satisfied total. And the grand total is the total number in our data set, period. Democrats, Republicans, lump them all in. All right. So now let's talk about, once you have the expected values, you have the observed frequencies, now you could easily find chi-square, right? Once you get your chi-square, how do you compare it to the chi-square distribution? Well, the nice thing is the chi-square distribution looks the same as in the test, as in the goodness of fit test. And so chi-square, it has a wall at 0. It can't be lower than 0. And it has a long positive tail. And when you decide on what your alpha is, that's what it's going to look like. Alpha is always one-tailed in a chi-square distribution. Excuse me. But the question is, how do you find degrees of freedom now that we have rows and columns? Well, the degrees of freedom is really going to be the degrees of freedom for categories times the degrees of freedom for however many populations or samples that represent your populations you have. And that's going to be the number of rows, right, because each category is in a row, minus 1, times the number of columns you have, minus 1. So that's how you find your degrees of freedom when you have more than one population that you're comparing. So what are the conditions for the test of homogeneity? Well, these conditions are going to be very similar to the conditions for goodness of fit testing. So the first thing is each outcome in each population falls into exactly one of a fixed number of categories. Well, the categories are mutually exclusive, just like before, right? You have to be in one or the other. You can't be in two categories at the same time. You can't opt out of being in a category. Also, the category choices must be the same for all populations. So one population has to have, if they have 3 choices, the same 3 choices must be the case for population 2. The second requirement or condition is that you must have independent and random samples. Before, in tests of goodness of fit, we only had this requirement that the sample had to be random because we only had one sample. Now we have multiple samples, and they must be independent of each other. They cannot come from the same pool. All right. So third condition, the expected frequency in each cell is 5 or greater. And that just is the same condition that we had for goodness of fit testing. It's because you want a big enough sample as well as a big enough proportion. And number 4 is not really a condition. It's just so that you know how free you are with chi-square testing. You could have more than 2 categories, and you could have more than 2 populations. So you could have 4 categories and 6 populations, right? So you could have a whole bunch of these different combinations. So you're not restricted to 2 categories and 2 populations.